Good morning, students. Let us start the class. Yesterday we had worked out one exercise on this common collector configuration using base bias. Now you are seeing on the screen one particular circuit. This is also common collector configuration or also called as emitter follower. But here you can see the voltage divider bias. We already know that the advantage of the voltage divider bias is the stability of the Q point. That is why in this particular exercise, voltage divider bias is utilized. But the analysis, the syllabus for the internals, I will tell you today. Don't worry, I will send the message in the WhatsApp. Don't worry. Today I will be finishing module 1. So definitely the complete module 1 will be there for the syllabus. If at all I cover module 2 little bit, then I'll let you know. Don't worry. By today afternoon, I will tell you the syllabus for the internals. Okay, let me continue the class. Here you are seeing the voltage divider bias for a common collector configuration. So except for this RB is replaced with R1 parallel with R2. Otherwise, everything is the same. So wherever we were using RB in the formulae, we are just going to replace RB with R1 parallel with R2. That's all. And we can check whether the approximate analysis is holding good or not by using the condition beta RE must be greater than or equal to 10 R2. And here, instead of that R0, he has given GOS. Actually, R is the symbol used for resistance and G is the symbol used for conductance. And ohms is the unit for resistance, whereas Siemens is the unit for conductance. So here he has given as GOS equals 20 microsiemens. A reciprocal of this itself is the output resistance for the collector to emitter junction. So using that, let us try to solve this problem. I will proceed quickly now because anyhow it is a repetition of whatever we did yesterday. So first we have to check whether the approximate analysis holds good or not. Now I have told you that R0 is nothing but 1 over GOS, that G is nothing but the conductance and R is nothing but the resistance. So 1 over 20 microsiemens. Don't confuse this with the seconds. This is not seconds. I have purposely put a capital letter there. If it is seconds, generally we use a small letter there. So it is not 20 microseconds, it is 20 microsiemens. That is the unit for conductance. So here R0 is 1 over 20 micro is nothing but 50 kilo ohms. Let us check for the condition. 200 into 2K, beta into RE is 400K. That is greater than 10 into R2. R2 is 8.2, so it is 82K. 82K is less than 400K. So the condition is satisfied, which means we can apply the approximate analysis. So using the approximate analysis, VB equals 8.2K into 20 divided by 64.2K. There is this 8.2K R2 into 20 volts divided by the total of 56 plus 8.2 is 64.2K. So we get VB as 2.55 volts. We can easily get VE and we can easily find out IE. VE is 2.55 minus 0.7 and RE is 2K. We get IE 0.925 milliamps. Now we can easily find out RE, small RE, that is 26 millivolts divided by IE. We get 26.11 ohms. Later on, all the formulae are one and the same. Only thing is for input impedance calculation, instead of RB, we have to substitute with R1 parallel with R2. So ZB is beta into RE plus RE. Yesterday we had seen. So that is 405 kilo ohms. So now ZI is 56K parallel with 8.2K parallel with ZB. That's what I told you. R1 parallel with R2 parallel with ZB. So we get input impedance as around 7.03 kilo ohms. Z0 is the same as yesterday's formula. So Z naught is, this R naught is there now 50K parallel with 2K parallel with small re, that is 26.11, which means Z naught is around 25.76 ohms. And
Sir,
AV
what is 405K?
405K, that is ZB. The input impedance with respect to base and emitter that we had discussed in the AC analysis.
Yes.
I have shown you on the top, that is ZB is 405K, that is beta into small re plus capital RE. Now remember this formula. Okay. So voltage gain is nothing but RE divided by capital RE plus small re. So we get voltage gain as 0.9871, which is approximately equal to 1. So yesterday I was telling, especially in the common collector configuration, we always get the voltage gain which is very much nearer to unity. That is why this is called as emitter follower. Or else you can see the input impedance is higher and the output impedance is lower. Can you explain Z0 once? Z0 is R0 parallel with RE parallel with small re. In yesterday's example, we did not use that R0 which was not given there. Now here, even if R0 is given, you will have to substitute it. See, we have an output resistance between collector and emitter. That is the internal resistance of the transistor. Then we have a physical resistance 2 kilo ohms. Then we have that small re, emitter's dynamic resistance. So please refer to yesterday's class where we had derived the expression for the output impedance. Output impedance is nothing but 50 kilo ohms is R0, that is nothing but 1 over GOS, that is given here. And this 2000 is nothing but 2 kilo ohms, capital RE. 26.11 is nothing but small re. So that is R0 parallel with capital RE parallel with small re. If R0 is not given, you can simply ignore it and you can directly calculate Z0 equals capital RE parallel with small re. But in this particular exercise, output conductance is given. Reciprocal of the output conductance is output resistance. Output resistance along with the emitter resistance, along with the dynamic emitter resistance. That is going to be the three parallel quantities. Let me go back to the previous slide where I had shown you the AC analysis. Look at this. Look at this. We have this RE and RE one end is connected to ground, and then we have this R0 across the transistor. That also other end is connected to ground, right? Because collector is nothing but AC ground. Then we have the small re which across the transistor. So we had derived the expression for the Z0, right? See, Z0 is capital RE in parallel with small re. When we derived this example, we did not bother much about that small R0 because it is always much higher than capital RE. But we are solving this here in this particular exercise only for the reason that in the problem he has given it. Even in yesterday's class, we had considered this 50 kilo ohms. You can see this here. And here in today's exercise, he has not given R0 directly, he has given conductance. We are taking its reciprocal and we are taking a parallel combination. Now you can work out your own exercise. Even if you ignore 50K also, there will not be a drastic variation in the value of Z0. You can calculate 2 kilo parallel with 26.11. And then you can calculate 50K parallel with 2 kilo parallel with 26.11. Whenever we have many resistances that are in parallel, now the effective resistance of the parallel combination is less than the smallest resistance in that particular combination. So you can see 50,000 ohms is there, 2000 ohms is there, and 26.11 ohms is there. So naturally, output impedance is always very much nearer to the least resistance here, 26 ohms, because other two resistances are much higher. There is a question that can you share this PDF after the class? I have already shared the PDF in the Google class. Please go through the PDF. In the Google class I have shared. Again today I will share the latest PDF. Complete module 1 PDF is there. That I will share. Don't worry. And so RE is internal to BJT. This I have told you how many times. Don't keep on asking the same questions again and again. The small RE, whenever we are using it, it is always internal. This I had told nearly 10 times till now. Whenever we use capital R, that is a DC quantity, physical resistance. Whenever we use a small r, that is dynamic resistance. That is why these R naught also is internal to the transistor itself. Because external resistors are used for biasing the circuit. Transistor itself has got a input resistance at the base to emitter junction. It has an output resistance at the collector to emitter junction. This I have been telling since so many classes. As soon as we started the AC analysis. You will have to revise all the previous AC analysis classes. I have been telling you repeatedly, at least daily 1 hour, you will have to revise all that which was taught for that particular day. Otherwise, on a daily basis, load will keep on increasing on your side because teachers will keep on covering the syllabus. And if you do not work out all these things at home, at least for 1 hour, if you don't study at home, then it will be a overload for you whenever you write a test or an exam. Don't take the second year syllabus lightly. I repeatedly tell you once again. I have not been seeing many students responding to my queries in the classes also. Except for 2 or 3 students, no one else is trying to solve the problems also. No one else is responding also. Even if you give me the wrong answer also, that is fine with me. But you should put efforts. But that I am not seeing as such in these online classes. So if you don't listen to my advice, you will have tough time when you face the test. Please remember that. Whatever is required for you, I am going to upload in the Google class. Even this PPT, I am going to upload into the Google class. That you don't have to worry. Even the PDF, the latest one, I am going to upload today. Don't worry. Textbooks I have already uploaded in the Google class. But your job is to study now. Fine. Enough of advice. Those who follow will follow. Those who do not follow will not follow. That is up to you now. Let me go to the next configuration. That is the last configuration called common base configuration. With that, we are going to end this particular module itself. So, AC analysis of common base configuration. Please recall the DC analysis of common base configuration where we had 2 power supplies. And I had told you at that time why we need 2 power supplies, because base is grounded and as base is common, we have to individually bias the emitter, we have to individually bias the collector. Now, in this example, he is showing a PNP transistor. So, its model can be directly written here. You can see as far as the AC analysis is concerned, all the power supply is nothing but AC ground. So, at the input you can see capital RE directly, and at the input you can see the small RE directly. There is no beta RE here. Why? Because the input is the emitter itself. Base is grounded. Between base and emitter, there is directly the dynamic resistance of the emitter. When we transfer it to the other side only, we multiply by beta. But here as base is grounded, we don't have to multiply by beta as such. We are directly writing this small RE. Next, at the output side, we have this alpha into IE. Why? Because the collector current is nothing but alpha into emitter current. You already know this ratio alpha is beta by 1 plus beta, that is always less than unity, because always emitter current is larger than the collector current. Why? Because IE is equal to IC plus IB. So, using that expression, revise your first year's basic electronics knowledge. And based on that, we have an expression for collector current, that is alpha into IE. And you can see here, the current direction does not change. So, we have written the same direction here also, which simply means that even in this circuitry, there is no phase shift as far as input and output are concerned. Now, at the output, again we have VCC. VCC we are shorting because it is AC ground. So, we have this capital RC. Now, looking at this equivalent circuit, the AC equivalent circuit of common base configuration, we can directly write an expression for Zi. That Zi is capital Re parallel with small re. At the input side, Zi is capital Re in parallel with small re. Now, at the output side, Z0 is Rc itself. Unless if just R0 is given. If R0 is given, that means the output resistance between collector and base, if that is given, then we can substitute that in parallel with Rc. Now, in this particular circuit, as R0 is not represented as such, in general, this R0 is really very high. You have seen in all our previous exercises, R0 is always 50 kilo ohms or more. So, it does not matter much. That is why at times if that is not given, we assume it to be infinity. So, in this case Z0 is Rc. So, now we will find out AV. AV is V0 by Vi. Now, what is V0? V0 is this current into this resistance. And what is Vi? Vi is this current into this resistance, whatever is the input resistance. So, it is alpha into IE into Rc. Alpha into IE into this Rc divided by IE into Re. At the input we have IE into Re. The value of this capital Re can be ignored. Why? Because the small re is always much lesser than the capital Re. Again I will repeat, when a large resistance and a small resistance are in parallel, the effective resistance will be always nearer to the smallest resistance there. So, when the small Re is in the range of 20 ohms, and when this capital Re is the range of, let us say, 20 kilo ohms, then we can always ignore this capital Re. That is the idea here. So, alpha IE into Rc divided by IE into Re, IE gets cancelled. So, the voltage gain is alpha into Rc divided by Re, small re. Now, as alpha is almost nearer to unity, what we can do is we can always approximately equate it to capital Rc divided by small re. But in the next exercise which I am showing you, we are considering alpha. Alpha is given there, and let us consider alpha and let us calculate the voltage gain. So, I hope you have understood this AC analysis of common base configuration. It is not really very complicated because we have already seen common emitter, then common collector, then common base. You may feel a little difficulty only with common collector or the emitter follower, because there are multiple junctions there where emitter is not connected to ground. But the only solution to that is go back to that particular notes or that particular slide in the video and again listen and try to understand. Even if you ask me questions also, I am going to tell the same thing again and again. Until you understand, I am going to tell the same thing again and again. Otherwise, there is no different answer for that particular query. Always answer will be same for the question. So, don't keep on asking me repeated questions. Okay. It is fine if you ask me questions. I have no problem at all. Any number of questions you ask me, hundreds of questions you ask me, I will answer. But don't ask me the same question again and again, which means you have not revised, you have not understood. There you have to put your own efforts in revising all these concepts. Okay, enough of advice and enough of big suggestions. Let me continue. So, let us solve the exercises now. Remember this formula, Zi is capital Ra parallel with small re for the common base configuration, and Z0 is capital Rc, and AV is alpha Rc divided by Re. Remember this only. You remember it as alpha into capital Rc divided by small re, because we are going to consider alpha. Now, using this, let us solve the exercises. Find Zi, Z0 and AV for a given common base configuration, where this is a PNP transistor. Naturally, for a PNP transistor, power supply has to be having a positive terminal, and at the other side the power supply has to be having a negative terminal. Why? Because in case of a PNP transistor, DC current flows into the emitter, and DC current flows out of the collector. That is why this particular symbol is given. Let me go back to the previous slide. Here you can see that emitter is connected to plus here and collector is connected to minus of the VCC here. Plus of the VEE and minus of the VCC. Later on, minus of the VEE and plus of the VCC are connected together. This itself we call it as ground. So, this has to be the direction of the power supplies. In case of NPN transistor, the direction of power supplies will simply reverse. If you apply a KVL here, from plus of VEE, current goes into the emitter and it goes out of the base. You have to apply KVL in this manner. Similarly, current that is at the output loop is going into the negative of the power supply because current is going out of the collector. In case of NPN transistor, the power supply directions will be fully reverse. So, the same circuit is written in a different way in this exercise. That's all. Don't get worried about all these conventions. What we do is, instead of writing the power supply or the battery exclusively, we simply put a symbol there. And we simply call this plus 6 volts as VEE and we call this minus 10 volts as VCC. And in this example, he has given alpha and he has given output conductance as 10 microsiemens. Now let us consider all these things. Let us apply the DC analysis also and the AC analysis also, and let us find out the input impedance, output impedance and voltage gain using the formulae which I mentioned in the previous slide. Anyway, I am only going to show you the answers because I am finding only that either Sayan or Lokesh or Harshit Gowda, only these three students have been responding to my exercises. The other two students, I don't know whether they are really listening to the lecture or whether they are trying out the exercise. I really don't know. All of you who are listening to the lecture have to work out these exercises. This I have been telling you the third time now in today's class. Please take this very seriously. Okay, let me continue. IE is 6 minus 0.7 divided by 6.8K. Look at the emitter. If you apply KVL here, plus 6 volts is applied here, that is across 6.8K, and then there is a base to emitter junction. Base is grounded. You visualize a power supply here or visualize a battery here. Now, if you apply KVL here, there is total 6 volts, but between base to emitter, there is 0.7 volts drop across the junction, and the resistance there is 6.8K. So, naturally, IE is nothing but 6 minus 0.7 divided by 6.8K. That is VEE minus 0.7 divided by RE. So, that is 0.78 milliampere. Once we find out IE, we can easily find out small re. So that small re is 26 millivolts divided by IE is 33.33 ohms. Next, once we find out Re, we can easily find out all other things. So Zi is 6.8K parallel with 33.3. This 6.8K is capital Re and 33.33 small re. Let me go back to the previous slide. Look at this. Zi is capital Re in parallel with small re. This we have discussed. And Z0 is Rc. And AV is alpha Rc divided by small re. Let us apply all that here. So Zi is capital Re parallel with small re. Naturally, you will get the effective resistance which is nearer to 33 ohms only now. Because 33 ohms is much lesser than 6800 ohms. So you will get Zi as 33.17 ohms. Now Z0 is here in this example as GOS is given. Let us calculate R0. R0 is 1 over 10 microsiemens, that is 100 kilo ohms. So now Z0 is this small R0 parallel with capital RC, that is 4.7K. That is Z0 is 100 kilo ohms parallel with 4.7K. We get the value which is less than 4.7K now. That is around 4.49 kilo ohms. Finally, AV, voltage gain, is alpha RC divided by small re. Alpha is given here. So let us substitute that. 0.998 into 4.7K divided by 33.33. So, students are waiting in the lobby. I will have to keep admitting them. So, next AV is 141. Now, look at these values and just analyze. We have seen common emitter where we had a voltage gain, and we had seen common collector where we had a high input impedance and low output impedance. Now look at the common base. In this common base, we have very low input impedance and slightly higher output impedance. This is reverse of what we expect from an amplifier. In general, in an amplifier, we expect very high input impedance, very low output impedance, and very high voltage gain. But in common emitter, we got very high voltage gain, but we did not get very high input impedance and very low output impedance. But in common collector, we got very high input impedance and very low output impedance, but we did not get voltage gain. Now look at the common base. Here only voltage gain is there. Input impedance is much lesser and output impedance is much higher or slightly higher. So we cannot use the common base configuration as an amplifier at all now, because input impedance is very low means whenever we give a very minute or weak signal, that signal will get loaded because of the low impedance of the circuit itself. I was telling you that input impedance of the amplifier must be very high, because the amplifier should not drain out any energy from the input signal. Whatever is the energy required for the working of the amplifier, it should be drawn from the power supply itself. But here you can see when the input impedance is hardly 33 ohms, if at all a picovolt signal comes or a femtovolt signal comes or a attovolt or a zeptovolt or a yoctovolt signal comes, you can imagine that signal will degrade itself, or the signal will have loss because of a very low input impedance. That is the reason we cannot use common base. Now, if such is the case, why should we use the common base configuration at all? There is an advantage here. The advantage is we will be working with so many such analog circuits. When we design electronic systems in the analog domain, we will have multiples of circuits, and you are going to study one particular theorem called maximum power transfer theorem in the course network analysis. In future, you are going to study that theorem. And the theorem briefly states that, I am briefly stating that power will be maximum when the impedance is matched. Means when the source impedance and load impedance are same, and that is when maximum power will be transferred from source to the load. Now, when we design so many circuits in our electronic systems, different circuits will have different types of impedances. Now, at many times, we will have to match the impedances of the two circuits so that maximum power can be transferred. Now, imagine a situation where we have a circuit, it has to be connected to another circuit, the first circuit having a very low output impedance, imagine that way, and the second circuit is having a high input impedance, imagine that way. Let me write a small block here now just to make it clearer. Let us say we have one system block and we have one more system block. Imagine, let me call it as 1 and let me call it as 2. Now, in this example, let us say the output impedance here is 33 ohms. Imagine here, output impedance of the circuit number 1 is 33 ohms. And let us say the input impedance of this circuit number 2 is around 4.5 kilo ohms. That is what is the example here, no? Around 4.5 kilo ohms. Okay. Now, as I told you, now this circuit has to be connected to this circuit. If this circuit has to be connected to this circuit, now the output impedance of the circuit number 1 and the input impedance of the circuit number 2, if they are same, then there will be a maximum power transference here. But in this particular case, the impedance is not matching. If the impedance is not matching, what we are supposed to do? What we do is, we will connect one more circuitry here. We will connect one more circuitry here. Now this circuit I will call it as this common base circuit. Whatever is this common base configuration, that circuit we will connect in between the circuit 1 and 2. Now this common base configuration has input impedance 33 ohms and it has output impedance around 4.5 kilo ohms. So 33 is matching, 4.5k is matching. That is how maximum power can be transferred from circuit number 1 to circuit number 2. Now that is the use of this common base configuration. Even though the voltage gain is there, it is not of much importance for us as such because of the impedance issues. So I had told you yesterday, whenever we want characteristics of the amplifier to be met, we will combine different configurations. So we can combine common emitter along with common collector, so that we will have high input impedance, low output impedance and high voltage gain. Now wherever we require impedance matching, there we can use common base configuration. That is the basic usage of common base. So with this discussion, let me proceed quickly to the next exercise, which is our last exercise for this module. The last exercise, only thing is the circuit diagram slightly differently shown. Otherwise, it is the same circuit diagram. It was horizontally shown earlier. Here it is vertically shown. And instead of PNP in this exercise, it is NPN transistor, which means collector will have a positive power supply and now emitter will have a negative power supply. Why? Because current will flow out of the emitter now. So naturally, VEE will be negative, VCC will be positive. Otherwise, everything else is same. Only thing is, instead of a horizontal view, you are seeing a vertical view of the common base configuration. As soon as such circuit is given, you should immediately identify that base is grounded, means it is common base. You will have to immediately identify. Then you should again think of this VCC and VEE and apply all the formula there again for solving this exercise. So let me proceed. IE is 5 minus 0.7 divided by 3.9K. IE is VEE minus VBE between base and emitter, that is that 0.7 volts, divided by RE, capital RE, that is 3.9K. We get I equals 1.1 milliohms. So small RE is 26 milli divided by 1.1 milli, that is 23.64 ohms. We can find out ZI now. ZI is 3900 parallel with 10 to the 0.64. Capital RE parallel with the small re. Naturally, you will get a value which is very much nearer to 23 itself. That is 23.5 ohms. Next, R0, he has given an output conductance 5 microsiemens. So R0 is 1 by 5 micro is 200 kilo ohms. Now for finding out the output impedance Z0, we can use this R0 parallel with the capital RC. That is Z0 is 200K parallel with 3.6K. We get a value which is slightly lesser than 3.6K now. That is 3.54 kilo ohms. Lastly, for finding out the voltage gain, AV is alpha RC divided by small re. So we have to find out alpha now. Alpha is not given, but beta is given. What is alpha? Beta divided by 1 plus beta is the formula for alpha. Now what is beta? Beta also you can find out using the relationship of alpha itself. You please revise the knowledge of basic electronics. We can find out alpha from beta, we can find out beta from alpha. That is possible. You will have to remember those formulae and you will have to always recall those formulae whenever required. So here alpha is beta divided by 1 plus beta, that is 75 divided by 76, that is 0.987. Now AV is alpha into RC divided by small re, that is around 150. This is the last exercise of this particular module. Now, we are coming to the end of this particular module. I have taken more than 9 hours now, but I went really very slow so as to cover all the basics as and when it is required. Otherwise, this module was supposed to be covered by 9 hours only, but I have taken nearly 15 hours now. But it does not matter. I wanted to have a strong foundation for this particular course. Always the first module will always take slightly larger time. But later on, I know where to go fast. Later on in the other modules, wherever there is always a revision of the previous basics, I will not spend much time in again revising the basics. So later on, we will be picking up the speed. It is not just the case with only me, it is the case with almost all other courses also, where first module we really go very slowly so that students will understand all the basic concepts. Later on in the next modules, we can go faster. So let me summarize the discussion which we did in this complete module. That is all summarized in this particular slide, which you can see. We have done the DC analysis for the biasing circuits in the beginning. Later on, we modeled the transistor using RE model. It is also called as pi model. And using this RE model or pi model, we performed the AC analysis and we found out the input impedance, output impedance and voltage gain. The DC analysis was meant for finding out the quiescent point or for keeping the transistor exactly in the middle of the active region, because that is the basic requirement for an amplifier to work. And AC analysis is basically for modeling the transistor in a linear fashion, where we used only a term called small signal analysis. And using this, what we will do in future is, we are going to use only the model of the transistor for all our future analysis. Whenever you come back to the college, when you start working in the lab, you will start working with that software called PSpice, which I have been telling you. And in that PSpice, you will simply pick up the symbol of the transistor and you will connect there. And the software will have the model of the transistor built into it. And that is how easily simulation is possible. You will have both types of experiments. You will have hardware experiments also, which means some of the circuits you will physically connect, taking a transistor and resistors, you will physically connect a power supply and you will measure its output and you will observe the output. After that, you will have a simulation also, where you will not physically use the devices, you will use the software for simulation. Our idea is that you will have to have some hands-on physically also, then you will have to have some hands-on using the EDA software also, electronic design automation software. That is the idea. Now let me conclude this module by discussing this particular table, where we are comparing common emitter, common collector and common base. We have seen in the common emitter configuration, voltage gain is medium. Medium means, let us say if it is above 100, but it is less than 1000. In such a case, we call it as medium gain. Actually, in an amplifier, we require a gain which is more than 100. Actually, we require 1000 or sometimes 10,000 or sometimes 10 lakhs also, because the input signal may be in femtovolt or attovolt. In that particular case, we want voltage gain which is much larger. But then it is not possible to obtain that voltage gain using a single circuitry. So what we do is, we do a series connection of common emitter along with common emitter once again. One more common emitter, one more common emitter, we connect them together, so that we will get a voltage gain which is in thousands or in lakhs. Later on at the output, we can connect a common collector. In the common collector, voltage gain is unity. But you can see, in the common collector, input impedance is very high, output impedance is very low. This is what we wanted, no? I'll annotate now. So, we are going to use common emitter for voltage gain, and we are going to use common collector for high input impedance and low output impedance. In between, we are going to connect many stages of common emitter for getting a high gain, so that we will have a high voltage gain also, and we will have a high input impedance also, we will have a low output impedance also. That is called as multi-stage amplification. Typically speaking, in your mobile phone, you will have minimum 4-stage amplifiers. Whenever it is going to pick up a radio signal from the free space, after the antenna picks up the radio signal inside your cellular phone, you will have at least 4-stage amplification happening there. That is what I meant here. So, voltage gain is medium in case of common emitter. It is unity in case of common collector. That's what is called as emitter follower. And common base, it is medium, which we have seen. But common base, we are not using it. Common base, we are using it mainly for impedance matching. I gave you an illustration of this impedance matching a few minutes before. Now, current gain in case of common emitter is beta, because input is at the base, output is at the collector. Current gain in case of common collector is also beta, because input is at the base and output is at the emitter. So, there is this beta factor, that 1 plus beta is there, that 1 we can ignore. But the current gain in case of common base is 1, because input is the emitter, output is the collector. Power gain in case of common emitter is high. Why? Because there is voltage gain as well as current gain together. So, when you multiply both of these factors, power gain in case of common emitter is high. Whereas in case of a common collector, it is medium. Why? Because only beta is there as a current gain. Voltage gain is unity. And in case of common base, as there is a voltage gain, but the current gain is unity. So, in both of these cases, it is medium. Now, phase shift in case of a common emitter is 180 degree. This I had already mentioned many times. In case of common collector and a common base, the phase shift is 0 degree. There is no phase shift between input and output, because the direction of current is the same. Impedance and output impedance we had already discussed many number of times. And lastly, application is common emitter can be used as a general amplifier, whereas if at all we use only the common collector, then we can use it as a buffer amplifier. Buffer means what? It will give only the current gain, it will not give the voltage gain. In general, buffer means output and input will have the same voltage or same amplitude, but output will have a more driving capacity as far as current is concerned. That means the amplifier itself is going to supply current to the signal. Now you can see the common collector configuration, the current gain is beta, so common collector can be used as a buffer amplifier, common base can be used for impedance matching, and common emitter can be used as a general amplifier. We can use all these three amplifiers whenever we want to use a multi-stage amplification, and we can also use the common base amplifier whenever we want to match impedance. With all these coverages of the topics, I am coming to the end of this first module, and I once again stress the importance of the revision of all these concepts again and again. Okay, this is where I am ending the first module. From the next class onwards, in the afternoon's class, I will start the second module. See you in the afternoon's class. I am going to the last slide. The last slide is all the best for your test. First module is complete. So, all the best for your test. Why that animation is not coming? Animation is supposed to come. Now the animation is coming. See, he is wishing you. He is smiling and he is wishing you work hard and give your best performance. Don't worry too much about the marks, but to worry about your own efforts and expect that I have done good justice for the coverage of the syllabus, as well as I have done good justice for covering the basics in this module. Now I expect the same amount of enthusiasm and effort from your side. All the best for your test and take care. See you in the afternoon's class.